In this presentation, what we're going to talk about is a new graph that we haven't had a chance to explore yet. Up to this point, we've talked about quadratics that created parabolas. We've talked about radicals. We've talked about polynomials. We've even talked about exponentials and logarithms. But now we're going to move into a different realm, and we're actually going to explore the graphs of a hyperbola. And the graph of a hyperbola is created by the parent function y equals 1 over x. So what I'd like you to do is take a moment to try to formulate your own hypothesis on what you think this actual graph will look like. Keep in mind that the graph itself represents all the data points that make this statement true. Now, as a preview, I'm also going to tell you that there's a few values that we know cannot exist. So that's going to have an influence on what our shape's going to look like. But take a moment, pause the video, and come up with your own prediction of what you think y equals 1 over x will look like. All right, so at this time, you've had an opportunity to go ahead and formulate your own opinion on what you think this graph might look like. So let's dive into a couple things. And one of the first things I want to look at is the fact that I have a fraction. So if I take myself back and I think about this function and having a fraction, I remember that in my domain or in the denominator, I am not allowed to have a certain value. And that value I'm not allowed to have is actually a 0. Remember, it's not defined if we divide by 0. So what this is telling me is basically that I cannot have an x value equal to 0. So what I'm going to envision is my vertical asymptote at x equals 0. I can put any other x value in there, but I can't put a 0. So let's think about some of those other x values there. Let's think about this for a second. And let's make it easy. Let's just say we substitute a value of 1 in for x. Well, if I substitute a 1 in for x, that's pretty easy. 1 produces 1. And then I could go down the ladder and I could pick a 2. Well, a 2 is going to give me a half. And then a 3 is going to give me a third. Which kind of makes sense that basically the larger the x value I substitute in, it's going to keep getting closer and closer to that x-axis. But now here's the question. Can I substitute a value in for x that would produce a value of 0? And that answer is no. No matter what I put in for x, it will never be actually equal to 0. It's always going to be equal to something. So that's an important fact for us to realize, because what that's telling us now again is the fact that we can never be equal to 0 as far as the y component is concerned. Because again, it makes sense if you look at it. If I have something, which is 1 in this case, no matter how many times I separate that or I divide that, there's always going to be something left over. So as we stated, if I separate that into 1 part, that's going to be 1. If I separate into 2 parts, it's going to be a half. If I separate into 3 parts, it's going to be a third. Now that portion gets smaller and smaller, and it actually will eventually basically be equivalent to 0, but it never actually is 0. Kind of interesting concept. Now let's go the opposite direction. What happens if I put, instead of a 1 in, let's go with 1/2. Well, now I have to actually remember that instead of dividing by fractions, I actually multiply by the reciprocal. So this would be a value of 2. So if I put 1/2, I get a value of 2. And if I put a third, I get a value of 3. And actually, the smaller the value I get, the bigger the number gets. So if we take a look at what's actually happening here, we get something that looks like this. It's kind of like a little curve that's actually happening there in our first quadrant, such that the larger the x value gets, the closer to 0 we become. And actually, the closer the x gets to 0, the bigger the y value becomes. But we didn't explore every aspect yet. because now that's just the positive x values. Let's take a look and see what happens then if we have negative x values. Well, if I put a negative in for x, let's just start off by substituting a negative 1 in. Well, that's going to produce a negative 1. Easy enough. And we could use the same thought process, such that if my value, actually the absolute value, if it gets larger, it's going to get closer to 0. Oops, it's kind of a bad shape there. And then as I get closer to 0, it's actually going to get bigger, but it's going to be in the negative value. Because again, I'm taking 1 divided by a negative, which is going to result in a negative. And this here then is basically our hyperbola shape, which will be the parent function for us when we have graphs that look of the form of a constant divided by x. Now, I'm not going to lie to you, that's not the best drawing. So let's look at what it possibly should look like if we were to graph something like this on a graphing calculator. And now you can see how we have that nice smooth transition such that as the larger x values come in, it get closer to 0. As we get closer to 0 on the x-axis, the values get larger. But now the question is, well, can we shift this graph? Or in other words, what would I have to do to this equation in order to get possibly this graph to appear in quadrant 2 and 4? Or better yet, how can I take this graph and shift it to the left 3 and up 1? Well, I guess you're going to have to tune into the next video to get that answer.